Time is the most measured quantity in our world. We use it to plan our lives, find our way, and make our fortunes. But measuring time wasn't always as precise as it is now in the 21st century. Just less than 100 years ago, time was in the form of pendulums and mechanical clocks. Nowadays, people can just look at their phones or computers to see a precise measure of time that everyone else sees. How did that happen? It all began in 1945. Isidore Rabi, a physics professor at Columbia University, focused his studies on the magnetic properties of crystals. That led him to spend 2 years working in Europe, collaborating at different times with some of the great scientists of the day, including Ernest Lawrence and Enrico Fermi. During the 1930s, physicists discovered the spin angular momentum, which generates a magnetic field and an associated magnetic moment in which electrons, protons, and neutrons act like tiny bar magnets with north and south poles. In his thesis, Rabi predicted that the magnetic moments of nuclei could be induced to flip their magnetic orientation if they absorbed energy from an electromagnetic wave of the right frequency. Using this system, physicists were able to detect and measure magnetic moments of the nuclei. The results made subsequent applications possible. One of those applications is the atomic clock. The National Bureau of Standards (NBS) was founded in 1901 and is one of the nation's oldest physical science laboratories and one of the world's prominent measurement infrastructure. Using Rabi's technique, NBS created the world's first atomic clock using the ammonia molecule as the source of vibrations. By 1952, it announced the first atomic clock, called NBS-1, using cesium atoms as the vibration source. From then, NBS developed a series of cesium-based atomic clocks. The most recent one was the NIST F2, which was launched in 2014 as a new U.S. civilian time and frequency standard, along with the NIST F1. Both NIST F1 and NIST F2 measured the frequency of a particular transition in the cesium atom, which is 9,192,631,770 vibrations per second, and is used to define the second, the international unit of time. The key operational difference is that F1 operates near room temperature, whereas the atoms in F2 are shielded within a much colder environment. This cooling dramatically lowers the background radiation and thus reduces some of the very small measurement errors that must be corrected in this F1.